Starting exactly at
Okay.
6:30. Welcome everyone who is gonna see this live, or maybe there will be a recording. I will introduce myself briefly. I'm Riccardo Poggi. I'm a physicist. I studied my majority of my life in Italy. Came at CERN for a summer student, technical student, and I just got my PhD with the University of Geneva. And now we have the pleasure of introduce to yourself and to show you the LEIR accelerator, the low energy ion ring. We have Mario already in the building, and I will leave the floor to him. He's the man. Mario, how's it going?
Okay. Well, good morning, everybody. So I'm Mario. I'm most Italian, by the way, but I'm also a physicist. But I done my PhD quite some years ago. I'm a bit older than Riccardo, so I am actually now a professor at University College in London, and I've been working on experiments at CERN for about 25 years. And I'm one of the members of the Atlas collaboration. So I work since about 15 years on Atlas, both trigger, hardware, and of course, analysis. So today I will be your guide for the next, say, about 45 minutes. And we'll show you around here in this hall, the hall that is one of the oldest places of CERN, that contains the LEIR machine and that contains the LINAC-2, that is the linear accelerator has been used for many, many years, and now has been just decommissioned because this year we start with LINAC-4 and so some other things in passing. So first of all, let me rotate the camera, and instead of showing my face, I really show you where I am now. So this is this big hole. I don't know because I understand that you are CERN alumni, so maybe some of you have worked here. Place. To give you an idea, this is next to the cafeteria of Building 6. The cafeteria is, of course, closed, and I show it to you now. This period of COVID, so half closed. There are not so many people around, and also, of course, it's Saturday. Right. So this is the hall. The hall is now a storage space, but this hall has been for a long time. This has been the place where people were making antimatter experiments at CERN. So nowadays, antimatter experiments are made done with AD ring, but for a long time, the accelerator, which is not LEIR, was actually called a LEIR, low energy antiproton ring, and it was used as a storage ring for antiprotons or storage. Why do you need storage? Of course, because as you probably know, whenever an antimatter particle meets its corresponding matter particle, the two will annihilate. So if you want to study the properties of antiprotons, well, you need to have quite a lot of antiprotons and send them against your detector. So you want to accumulate protons, and if you keep them going around in air, they will sooner or later meet some proton and annihilate. While if you keep them in vacuum, then you keep them for several hours, and the just a very small number of these antiprotons will somehow be lost. So this area, which is, as you see now, a storage space, used to have, let's say, when I came here for the first time, it was around 1995 or so. It used to contain a lot of experiments that were comparing properties of matter and antimatter. But then, as I said, I mean, nowadays, all the antimatter experiment has been moved about 500 meters in that direction, because there we have the new antiproton storage ring, which is called AD. And now, since about 2 years, we have a brand new machine, which is called Elena. It's even smaller than the AD, is even lower energy. Why that? Well, because strangely enough, when you want to study antimatter, instead of accelerating particles, you would try to decelerate them. You would like to have them at the lowest possible energy. So they have built this AD machine that actually is coming from an older accelerator. So many of the magnets are the magnets from the ISR, the old ISR accelerator. That was the first proton collider in history. And then also some parts of that come from the old demonstrator that was used to demonstrate stochastic cooling, because indeed the AD area is a place where stochastic cooling has been demonstrated for the first time. But right now, let's go to this platform and I will show you the LEIR ring, the low energy ion ring. So I'm getting there. Here it is. This LEIR, I don't know if you have seen it already in person. This actually is one of the smallest accelerators of CERN, and it's not even circular. You know, most of the accelerators are circular. This is almost squared, but it contains all the elements of a normal particle accelerator, namely dipole magnets, which are these orange objects that are used to produce a vertical magnetic field, and this vertical magnetic field will make the particles turn. Then there are the quotable magnets, which are this bluish sort of cubes, and then we have the accelerating cavities. So we have some cavities here, but these are not accelerating cavities. These are cavities that are used for phase shifts. So if you have a beam which is mainly which has quite a large say longitudinal distribution and a small transverse distribution, using this kind of cavities you can reverse this these distributions, and then that's actually used quite often in the beam optics. While the accelerating cavities are located in the other straight section, which is here. You probably know that indeed all the accelerators have curved and straight sections. Also the LHC is made of 8 arcs and 8 straight sections. The difference with respect to here is that here the straight sections are longer than the arcs, while on the LHC, well, the arcs, the straight sections are 300 meters each, and then the arcs are about 8 kilometers each. So clearly, the LHC is almost circular, even if it's not really a perfect circle, and this is almost square, even if it's not a perfect square. Another interesting object they have here are these 2 towers, which are the stochastic cooling system. So you probably know what the stochastic cooling is that you are, sorry, it's not stochastic cooling, this is electron cooling. This is the electron cooling system. This machine is too small to have a proper stochastic cooling. The electron cooling means that you're sending in the beam some electrons with a very, very narrow energy spread. Like this, the electrons can reduce, they will increase the energy spread, but you don't really care about the energy spread of the electrons. But the interaction between the beam and the electrons will reduce the energy spread of the normal beam, of the ion beam. So this machine was built in the early 80s. It was called, as I said, LEIR, low energy antiproton ring. So here, antiprotons were circulating, and then were sent on the other side of this wall, where, as I said, there were several experiments to measure the properties of antiprotons, so the properties of antimatter. But then, after the antiproton physics has been moved to the AD, this ring has been recycled for the LHC. So you may know that LHC does not only accelerate protons, but also heavy ions. Actually, I think that if the LHC was only proton collider, it would have been called LPC, Large Proton Collider. While it's called Large Hadron Collider, because for about 1 month at the end of every year, we do accelerate lead ions. So lead ions are used to measure, let's say, very high energy nuclear physics. So it's quite a different kind of physics that we do with protons and we do with lead ions, because protons, well, they're not elementary particles, but they're almost elementary particles. So when we collide 2 protons, basically we collide 1 quark or a gluon from one proton and 1 quark or a gluon from the other proton. While when we collide lead ions, the size of the nucleus matters, and also the impact parameter of the nucleus matters, because there are some peripheral collisions where only a few protons from one ion collide with a few protons from the other ion. There are central collisions where you have the whole nucleus, almost the whole nucleus that collides with the whole nucleus on the other side. There are effects, pressure effects. There are effects of high density of nuclear matter and so on. And this is the study of nuclear the lead ions is done because we want to study the properties of a quark-gluon plasma. Quark-gluon plasma is a phase of the life of the universe where basically the whole universe was a soup of quarks and gluons. So today we don't see free quarks or free gluons. Quarks and gluons are organized into hadrons like protons, pions, neutrons, and so on. Well, there was a phase, quite short phase of the life of the universe, where the universe was just made of quarks and gluons. So we want to study the properties of this quark-gluon plasma. In order to do that, we accelerate lead ions in the LHC. We not only accelerate lead, we do also accelerate other nuclei like xenon and maybe oxygen. But lead is really heavy, and it's relatively easy to produce. So yeah, I mean, most of the program is done with lead. Right. So you probably know that protons are accelerated in a 5-stage sequence. So the first acceleration of this proton happens with linear LINAC, a linear accelerator. The LINAC we use so far is the LINAC 2, which is located somewhere over there, and I will show you the LINAC 2. From next year, we'll use LINAC 4. Actually, from this year already, we have used LINAC 4, even if we are not really, we haven't started LHC this year. And we'll just start LHC in October for a short pilot run. That will be about 3 days, actually 3 shifts. And that's it, right? I mean, we won't be able to even accelerate the protons in the LHC this year. But then we'll start in earnest next year with LHC. In LHC, the protons are, as I said before, first accelerated by the LINAC 2, then they go to the booster. The booster, we don't see the booster, but this is quite close to where I'm standing. It is somewhere over there. Then from the booster, they go to the PS, the proton synchronotron, which is somewhere over there. Then they go to the SPS, and then finally to the LHC. There's 5 stages. Lead ions are also accelerated in 5 stages. However, since the mass is of lead is much larger than the mass of a proton, for lead ions, the ratio, the energy to momentum, to velocity ratio is very different with respect to that of the proton. So we need an accelerator that's tuned in quite a different way than the accelerator which is used for the protons. And that's why we cannot really use the same linear accelerator. So we have to use the LINAC 3. LINAC 3 is located somewhere over there. And then we need to use a different first stage circle accelerator. We don't use the booster, but we use this LEIR. Right. So before changing this machine, before changing to LEIR, when it was still an anti-proton storage ring, this machine became quite famous worldwide because this is the place where, for the first time, anti-hydrogen has been produced. Now we produce large quantities of anti-hadrons. Well, large quantities. I'm talking about the order of 10,000 or so every fill in the AD. But at the time, nobody had ever managed to produce bound states of antimatter. And so this experiment even got the first page of the Time magazine. There was 1995 or 96. And it was quite a clever way to do that. So I can show you a schematic view. So this is when the machine was LEIR. And it was studying antimatter. So recognize the shape of this ring, this square shape. You see the straight sections in blue and the arcs in orange. So when people wanted to test the production of antihydrogen, um, they had put here in the middle of one straight section, they had put a jet of xenon gas, and then a detector at the end. So why that? Well, first of all, like xenon, because xenon is a noble gas, so it has large. Well, first of all, doesn't have too much chemical interactions, but on the other hand, among the noble gases, is one with the largest atomic number. So it has quite a large electrical field between the nucleus and the electron. So the antiproton from the beam was interacting with the xenon. It was interacting with the electrical field of the xenon, and then it was sometimes producing an electron-electron pair. In that case, well, rare but finite number of times, the antiproton and the anti-electron were going in the same direction, and the anti-electron was captured by the antiproton, producing neutral antihydrogen. Now, you see the arcs are there to bend the particles, but the particles are bent because of the Lorentz force. So a particle which is neutral will not be bent by the Lorentz force, will go straight. So there was a small hole made here in the magnet that was allowing neutral particles to go through. So already the fact that there was something here, something that was not deviated by the magnetic field, was the indication that perhaps the production of neutral antihydrogen has taken place, but it was, of course, not sure, right? It was not obvious. Was You had to demonstrate that. So in this experiment, after production, antihydrogen was immediately destroyed. So this experiment was not aiming at measuring the properties of antihydrogen. The experiment was just aiming at demonstrating it was possible to produce antihydrogen in the lab. So in order to demonstrate that, antihydrogen was destroyed just a few meters after its production. So the antihydrogen atom was going to the germanium detector. There, the external anti-electron was annihilating with the electrons of the detector, producing two gamma rays, so two photons with a characteristic energy of 511 keV, that's corresponding to the electron mass. And then the antiproton alone could continue its path. It was measured by magnetic spectrometer. Then eventually it was also destroyed and annihilated. So as I said, the production of antihydrogen was followed by its destruction. There was no aim at measuring the properties of antihydrogen. Well, now in the experiments at the AD, we indeed do want to measure the properties of antihydrogen. That's the aim, and I want to compare the properties of antihydrogen to those of hydrogen. And in particular, well, we want to measure, and we have measured the spectral lines of antihydrogen. So we have measured basically the electromagnetic field, the properties of the electromagnetic interaction for antimatter, and they were compared to those of matter, finding so far very good agreement, even if the precision that we have on the spectral lines for antihydrogen is of the order 10 to the minus 12, while the precision we have now for the spectral lines for hydrogen is 10 to the minus 15. So we still have a 1,000 times more precision for the studies of matter than for the studies of antimatter. But nevertheless, I mean, so far the two measurements are in agreement. And as expected, we believe that electromagnetic interactions are the same between matter and antimatter. All right. So now I'm going down a little bit because I would like to show you the LINAC 2 and like to discuss a little bit about the proton source and the production of protons at the first stages of acceleration. So to do that, I have to go down 2 sets of stairs. I arrived. So now the screen got back. Are you still there? You still hear me? Hello? Hello? Can you hear me? Hello? Hello? Ricardo? Hello? 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 Do you see me? Do you hear me? Hello? Hello? Ah, all right. Sorry. Good. Because I think I've lost the connection a little bit because here. And it really looks like a control room from a science fiction movie because it's from the 60s and well, maybe 70s. And it's still used. This is still operational. I mean, all the controls of CERN accelerators now have been centralized in this big control room, which is located in Prevessin, just next to the entrance to the left or the Prevessin side. However, there are still some operations that can only be performed in this control rooms. If you want to change some fundamental parameters of the machine, you still need to do it from here. And this is why this control room is not dismantled, but it's still here. And it can still work. But you don't really see people shift here. You don't see many people working here very often. On the other side of this door, so I cannot enter, by the way, this is closed. Is reserved to authorized person. I'm not authorized as a guide, just as a guide. And then, but on the other side, so you see there is this wooden door, and then on the other side of this wooden door, there is a metallic, big metallic container. This is the proton source. This is the place where the proton start their path. This is actually the old proton source because this is the proton source that was attached to LINAC 4. LINAC 2, sorry. Now we have LINAC 4. So there is a new proton source, and so this one is not really operational anymore. I don't know. Maybe at some point it will be possible to really have visits of LINAC 2. I don't know. You see to the left, there's this blackboard, and here somewhere there is this red a gas tank. This is a tank of hydrogen. This is where the protons are produced. So protons are coming from hydrogen gas. Then this hydrogen gas goes, it's basically a tank you can buy in a shop, right? Then it's sent to a low pressure chamber. And there you have a strong electrical field. You can separate protons from electrons. Then the electrons are sent to a grid, so they are absorbed by this grid, and the protons can start their path. They pass the grid, they enter the first instrument, which is a radio frequency quadrupole, and then they finally enter the LINAC accelerator. So why do we need a radio frequency quadrupole, and how does it look like? So this is the old radio frequency quadrupole of LINAC 1. So you see, this is how it looks like. It's like a cross. And here we have electrodes. This instrument is used to both focus the particles and accelerate them. And it's actually important. Normally, in an accelerator, we have radio frequency cavities that are used for acceleration and quadrupole magnets, which are used for focalization. But here in this instrument, we have both. Why? Because the particles have very little energy, and therefore they need to be accelerated, and also they are coming in large amount of different angles. So you need focalization. If you, well, it's like in a lighthouse, right? In a lighthouse, you have a lamp, and then the lamp will produce light that goes in several directions. But then you have a lens, and as this lens is making is focusing on the light, and then you have a parallel beam of light, and this is quite similar here. This radio frequency photoball will produce a parallel beam of protons at the same time. It will accelerate them. So see from this panel, you have both acceleration and focalization. This is done by having alternating electrical fields because these electrodes, these four electrodes can be put at the potential. So typically what happens is that two opposite electrodes are put at the same potential. So you have either this positive, positive, and negative, negative configuration, or negative, negative, positive, positive configuration. These two configurations will squeeze the beam in one direction or the other. This is how you do the focalization. But at the same time, this is done in an alternating way so that you can also create a field that is going in the z direction, so in the direction of the beam, a field that is pushing the particles and is accelerating them a little bit. But then the proper acceleration is actually done by the cavities. So here I'll show you one of the cavities from LINAC 1. And actually, if you've ever been to the microcosm, there's a very beautiful set of cavities from LINAC 1. It's basically the first room as you enter to the left. Now you can see all these cavities, and they're quite impressive because there you see that these cavities change shape dramatically because the protons are getting accelerated, and then they will be faster and faster. So here, what can we see? Well, we can see first of all this little hole. That's the hole for the beam where the protons of the beam are going. I put my finger here to show you the size. So the diameter of this hole is maybe 2 or 3 millimeters. And then here we have this cavities. What really matters is the space between the cavities. The cavities can be electrically charged. So there's a production of an electrical field between one cavity and the next. But then this electrical charge of the cavities is alternating. So we have this field, which is between the cavities here. This field will alternate between positive, negative, positive, and negative. Why that? Well, because first of all, having this field and having this alternating field will produce bunches. We don't want a continuous flux of protons. We want protons to be divided into groups, into bunches. Why that? Well, that's because like this, it is easier to accelerate the protons. And also, when the protons collide in the detectors, they're not colliding all the time. We know exactly when the protons are colliding, then read out the detector, and then there will be some time where the detector can be read out without collisions, and then the next collisions arrive. So we really want to have a bunched beam. So the bunching, the separation of the protons in bunches is done by these cavities, and also basically what we do if we. I mean, the reason why these cavities are alternating, the reason why the voltage of these cavities is alternating is because like this, if you look at a region between two cavities, you will see, as I said, an alternating field. So you see an electrical field that goes positive, negative, positive, negative. But this alternation, this change of field is also in phase with the time it takes for the bunch of protons to go from one cavity to the other. So if there's a bunch of protons here in the first gap, there will be a positive field and the protons will be accelerated. Then in the second gap, there will be a negative field. But the protons, so the protons will be slowed down if they enter negative field. But the time it takes for the protons to move from the first gap to the second gap, well, is the time needed for the field to change orientation. So when the protons enter the second gap, there will be again a positive field that will push them again, and so on and so forth. So if you're following the gap between the two cavities, there you will see an alternating field. So you see an alternation between positive, negative fields. If you follow the bunch of protons, well, there you will, the protons will always find themselves in a region with a positive field. So it's like a surf, a wave on the sea, right? If you look at a fixed point in the sea, like a buoy, then you see the buoy will go up, down, and because the wave is just perturbation of the surface and it will oscillate. However, a surfer will move together with the wave. Therefore, the for the surfer, the crest of the wave will always be behind, the bottom part, lowest part of the wave will always be in front, and that the first surfer will be able to get energy from the wave and move with the wave. And that's exactly the same thing happening with the protons that are moving and getting accelerated by these alternating fields. Another thing worth noticing is that here you see that the cavities are getting bigger and bigger as they move away from the beginning. It's maybe not very easy to see. Probably you can see it if I yeah, look from the side. So these are the cavities at the beginning of the cavity of the structure, and these are the cavities at the end of the structure. There's not an enormous difference, but they are definitely bigger. Why that? Because particles are accelerated by this cavity system, and when they accelerated, they will travel more space in the same unit of time. And then, so in the same acceleration, in the same period, when the field changes, the field will change at the same time in all the cavities. Therefore, during this period, the particles will have traveled more time, and we need to have more distance between a cavity and the other. All right, so now let me move a bit more, and I can show you the LINAC 2. Are you still there? Because I lost the image from you.
We are still there. You're still. We can
Okay,
hear
very
you.
good.
We are following your
Perfect.
explanation. Everything is working. Thank you.
Okay, great.
So those are very interesting pieces of machine that you are showing us, by the way. Very, very nice.
You've been here? Do you know this place?
Yes, a little bit, but it's nice to follow your explanation, to be guided for once.
Okay. So from here, we can see a bit better the box. That's the proton source. This is a metallic box that you see there. It's really the beginning of the path of the protons. There's nothing behind it. That's really there where the protons are produced and they're first accelerated. Then they go, well, we have a wall, so we don't see very much. But here, there's a door leading to LINAC 2, and I cannot enter because it's probably still a bit radioactive, but I can definitely show you LINAC 2 from this window. And it's quite impressive. It's quite an impressive machine that's worked for maybe 30 years or so, maybe more, being the first really stage of the acceleration of the protons that end up in the SPS and then in the LHC. While at the time of LEP, there was yet another acceleration system. It was called EPA, Electron Positron Accelerator. So this was always the proton source, but it was never the electron source. Okay, now I'll move back and I will go and give a look at the Roy Billinger room. That's the room where we have the screens that show the situation of the various accelerators. So I don't know what the current status of accelerators is because, well, this year is a strange year in a way, because this year we're not running the AC apart from this pilot run in the end of October. However, we are running normally the PS and the SPS, but I don't know if they're running today. Since I'm here, I also wanted to show you this access door. Many of you, if you work at CERN, you don't know how it works. But the idea is that if you want to access an area that is controlled, an area where in principle you can have radiation, you can have a beam, well, not everybody can enter freely, of course. The access is controlled. And there are these doors that show the situation of the possibility of entering or not this area. So currently the area is closed, so nobody can enter. Maybe there is beam, maybe there is radiation. I don't know why, but anyway, nobody can enter. In some special and particular cases, especially where people are working on, installing or removing equipment, you can be in green. General green means that everybody can enter. In this case, normally they open this red door over here, so everybody can enter or exit from this red door. When the beam is not there, but they want to still control who is entering the experimental area, the access is restricted. So when the access is restricted, people can enter under conditions. So that means that in order to enter, well, you need to enter for a reason. So you will swipe your card or your dosimeter here. You will talk to the control room, telling them why you want to enter and for how long you want to stay. And then you have to take one of those yellow keys. Why that? Well, it's a very simple but quite efficient safety system. The machine cannot be restarted unless all keys are back. So if you are working inside the experimental area and you have the key in your pocket, you know that nobody can restart the accelerator even by mistake. Of course, you have to remember to bring the key back, because if you go home with your key, the machine cannot start at all. But okay, it's always better to be too cautious that too little. And then once you have taken your key, then you can enter. There's a buffer zone where they will scan your iris, the iris of your eye, and so they will, you'll have the authorization of entering the experimental area. So this safety system now is the same also for the LHC. So I went down to the Atlas Cavern recently in the last couple of days. It's a bit painful because not always working properly, but yeah, I mean, it takes some time. At the end, it works. At the end, you can enter. So I'm going. So well, there's not much going on, but the SPS is running. I don't know why the PS screen is off. I'm trying to switch it on, but no, it's not working. I don't know. Anyway, let me show you the SPS screen. Maybe some of you are already familiar with how it works. It's quite interesting because here shows you the cycle, the SPS cycle, the last about 17 seconds. So we have this vertical line that is moving through the cycle and is indicating where we are in the cycle. And there's other two shapes, strange shapes. One is white, one is yellow. So the white one represents the current in the magnet. So basically the energy of the protons in the machine, while the yellow one represents the intensity of the protons. So you see that whenever the vertical line moves, then it means that the number of protons is given by this line. The number of protons can also be seen here at the top by this number, and this is the energy. So what we see here in the beginning of the cycle, when the line goes here, then there's an injection, because the number of protons that was very small has two jumps. There are two injections from the PS to the SPS. Then once the protons have been injected, once you are in this position here, then we start the acceleration. So we start increasing the magnet current. So we start increasing the energy of the protons. Once we reach the maximal energy, then we start to eject the protons. So this is a slow ejection. And then once you finish, when the number of protons is very small, then we lower the current in the magnets again. So there, I don't know what is this little spike. At some point, they increase the current and lower the current in a second or so. But after that, we have another cycle of acceleration, so injection, double injection, and then here acceleration, and from here on we have the slow extraction, all the protons and so on. So here, basically in this cycle, in 17 seconds, they have two slow extractions. They have two accelerations and two slow extractions. The cycle can be different. It really depends on the program. It really depends on the experiments that they have to serve. So in this moment, the SPS is just used to feed compass and two test beam lines, H2, H4, and H6, H8. And A62, target 10, I see that there's zero, so this moment they're not sending protons to an A62s. But it really changes because sometimes the SPS is accelerating protons for the LHC. Other times they're using it for different experiments and so on. So the cycle for the SPS is decided during the run meetings on a daily basis, and then it depends really on the physics that you want to do, on the experiments that you need to feed. All right, so we're almost finished for this visit. The last room I want to show you that's close to the cafeteria is the satellite CMS control room. So actually, before the shutdown, there was a large satellite control room. There was here, it was this one. But now they decided don't really need such a big room. So this area has been converted into offices. And then the satellite control room is smaller, but still there. It's here. Of course, there's nobody there because we are not taking data. And there's no point in staying here in the control room. So why satellite control room for CMS? Well, as you can imagine, all the detectors, they have their own control room. And clearly the control room is next to the detector itself. So in Atlas, we do have the control room where we have the Atlas Visitor Center quite close to the globe, on the other side, respect to the globe. And also LHC, ALICE, and CMS, they have the control room close to the detector. However, the point is that CMS, as you probably know, is quite far away. It's about half an hour driving in CC, so towards JAX. And you know that during data taking, a lot of things can happen. So we do have shifters that take 8-hour shifts. And so you have shifters 24 hours a day in the control room. But you not only have shifters, you also have experts. You have people who are there. They have their CERN cell phone, and they can they have to intervene whenever there is a problem. So whenever the shifter finds a problem with the subdetector, the expert of that subdetector is normally called. Usually the expert can do things just with the computer, but sometimes the expert has to go to the control room. And can you imagine, I mean, if every time that there is a problem, the expert has to drive down to CC, and then if the problem is serious, you may lose, say, half an hour of good data just because the expert is driving. It's not very practical. So they have decided to have a satellite control room here in the center of the Marin site, such that the expert could actually come here rather than going to CC. That actually was quite useful because that allowed really quick intervention. But as I said, nowadays, most of the interventions can really be done from anywhere with a laptop. So that's why they have shrunk the control room. It's much smaller than it used to be, the satellite control room. Okay, so that is roughly all I wanted to say for this visit. So it brings me to an end. Do you have questions or comments?
Thank you very much, Mario, for the nice tour of the facility. It was very comprehensive and instructive. We got to see many things. I found it quite interesting. I would like to invite anybody that might be following to post their questions in the chat, and I will relay them to Mario. In the meanwhile, I have a couple of questions. that arose quite spontaneously from what you showed us. Maybe the first one, since you're there, you showed earlier the access and the safety features, more than security features, on how to enter the accelerator, and you showed us that at the moment it's not possible to enter; it's closed. So someone might ask, oh, it might be working, you even said, and someone might ask, well, isn't it dangerous for you to be there at this moment? You are very close, or maybe not so close, depending from the point of view, but you are, it's an open accelerator, so maybe can you tell us? And there are also a few lights around that maybe you can also show us.
Well, you see that there are anyway these very thick concrete walls. The concrete walls are there because of for shielding. So I actually never, it was always on the other side of the concrete walls. And yeah, the lights you're referring to are probably this, sorry. Yeah, they're probably these units, these radiation control units. So you see they are green, means they have no radiation. Otherwise, we would hear an alarm. Sometimes you get a red sort of light happening, but this is only because there is a cosmic ray passing, a cosmic muon passing. We'll have a very short burst of red light, but this doesn't mean there is any radiation. When I was on the top of the machine, then I would not have any radiation because the radiation would be contained to the plane or not. Is completely safe. I don't know. I don't think there is ions. Other reasons to block the access to people.
Yeah. Yes, perfect. It was just someone might have the curiosity of knowing. Well, you were quite close to it, but yes, perfectly. You were perfectly safe, and there are the system in place. Then you showed us also the various panels about EPS, and you also mentioned how well the LEIR accelerator is integrated with the LINAC 4 and the PS and the whole structure. So there is a complex schedule for operating these accelerators, all this complex machine. When is the LEIR in its most productive time? You mentioned a bit about the operations. So
yes, around November normally, not this year, but normally around November, at the end of the year, at the end of the LHC exploitation, then we have the heavy ion run.
Yeah, and which experiments do partake into these massive collisions?
All of them. Alice is specialized in the heavy ion, so Alice has this big TPC that is very slow. So Alice cannot run at full intensity runs, but it is still run during photo runs, but is somehow dedicated to lead ions because of this TPC. On the other hand, the other experiments, even HCB, now take data and have publications with lead ions. They have specialized groups that are working on lead ions, and because we, on the other hand, have a very good calorimeter. So Alice is a very good tracker specialized for lead ions, while in others in CMS we have very good calorimeters. So we do say different measurements during the lead ion run. They're quite complementary, actually.
Yes, indeed, it's very interesting physics as well. So that concludes the questions that came to mind. It seems like you've been very thorough, so I'm not getting further questions from the audience.
Okay, very good. So bye-bye, everybody, and have a nice continuation of this workshop.
Okay.
Okay.
Thanks, Mario.
We can close with an image of your workshop. I just saw it here.
Perfect.
All right, I think that's a nice image to close this meeting. Bye-bye.
Thank you, Mario. Bye-bye. I will close the meeting.